We're going to test the starter motors. We're just going to do a bench test. The first thing that we've got to point out very, very importantly is this starter motor has got permanent magnet fields, and we must never ever clamp that in a vise, because as soon as we do, it'll distort those fields, it'll either dislodge them or crack them, and the starter motor has had it. So whenever we've got a permanent magnet field starter motor, make sure that we clamp it by the housing. We'll connect our ground terminal to the body. We'll connect our positive terminal to the battery positive. Our jumper wire to the solenoid terminal, and then we bridge that to positive. As you can tell, this starter motor's actually got a fault. The first couple of times that we activated it, it wouldn't spin. So this one is in definite need of repair. The next starter motor we've got has got a wound field. We can tell it's got a wound field because it's got these large screws sticking out the side which hold the fields in. These we can quite safely clamp in the vise. Same thing, we connect the positive battery, if we can. We connect our negative, and then with our jumper lead. Can you press the button for us? Now, even though we've done a dry run test on this, one thing we haven't done is loaded it up. We cannot guarantee that this is going to work in the vehicle properly. Without that loading, we can't tell about the solenoid contacts. So if this was going to go in a vehicle, we would still need to dismantle it and test all of the components individually. We're going to test an inertia drive starter motor. We connect the negative to the body, we connect positive to the motor connection, and remember that we need an external switch because if those leads are live, it'll rotate straight away. And you notice that once it started running, as soon as it reached top speed, the inertia drive pulls back out of mesh because it relies on the torque between that and the ring gear to keep it running.
Here we have the internals of an inertia drive starter motor. You have your armature and your drive pinion. If we see here, when the armature is rotating, the drive pinion will overcome internal spring and, guided by the helix gear, will mesh the pinion with the ring gear. With the inertia drive starter motors, you'll find externally mounted solenoids. These here will have a battery supply in, a permanent ground, and a positive actuation. When the key or start button is pushed, the little solenoid will distribute battery power down to the starter motor. In this section here, we're looking at the inspection of the armature. If we look closely here, we can see a darkness around our armature. What that is a problem known as poling, whereby the bushes which support the armature have worn and caused the armature to make contact with our field shoes. If you look closely on the windings here, you can see a discoloration caused by overheating of the armature. With the commutator, checking it here, it's nice and square, no signs of excess wear, but unfortunately, due to the overheating and the poling, this armature will need to be thrown away. Getting there, I was going to say due to the excessive wear, Alright.
Yeah, start again.
I need to okay this video before it goes online. Or before you submit it.
Just move it forward a touch, if you would. Yeah, good.
So looking at this commutator here, we can see there is extreme wear on the commutator caused from contact with the brushes and a long-term use. This commutator is beyond repair and will need to be turfed with the armature. Another important check when inspecting the armature is to inspect where it sits inside of the bush in the end housing. Look for any signs of wear, any lipping on the shaft.
Okay.
Here we have our 12-volt solenoid ready for bench testing. We're going to check the pull-in and hold-in winding resistances. First of all, the pull-in winding between our start terminal and the motor side of our solenoid contacts. We have 0.5 of an ohm. To check the hold-in windings, we go between our start terminal and the body of the solenoid. And we see there 1.5, 1.6 ohms. So after measuring resistance, we want to physically check the operation of our solenoid. I have my negative cable connected to the motor side of the solenoid, and I have a 12-volt fused supply for my start input. There we see our pull-in windings functioning correctly and pulling the plunger into the solenoid. This time we'll be testing our hold-in windings. I have a negative which I connect to the casing of the solenoid. Here I have a switched positive input which will go to my start terminal. You can see a little bit of induction there. First I have to overcome the spring tension that's holding the solenoid plunger out. We can see the solenoid plunger clicks in place, bridging those contacts internally. If we release the power, the plunger returns. Here we have our solenoid removed from the starter motor. We'll be checking the resistance of both the pull-in and hold-in windings. For the pull-in winding, we go to our start terminal and to our motor side of the contacts. We have there, when it settles, about, settle down, 0.5 of an ohm. To check the hold-in windings, we stay on our start terminal and go to the body of the solenoid. And there we have 1.8 ohms. On this solenoid, we'll be checking the pull-in and hold-in windings. First of all, the pull-in windings. I have a positive supply connected to the motor side of my solenoid and a negative to my start terminal input. We can see the plunger actuating. Next, we'll be checking our hold-in windings. I have an earth to connect to the casing of the solenoid and a switched positive input to my start terminal. You can see there's a bit of an induction there. If I try and overcome the internal spring, we can see here the hold-in windings are not functioning on this solenoid and we will need to be replacing this solenoid. In this demonstration, we'll be inspecting our starter motor contacts. We remove the end plate. Here we can see our starter solenoid plunger. Here is our contact disc. We should inspect for signs of wear and pitting. Here we have our main starter motor contacts. This one being your battery input side. If we look, we can see that there is excessive wear on that contact. That would need to be removed and replaced. When you have the starter motor dismantled, it's always important to inspect the pinion drive for signs of chipping, missing teeth, any sort of wear. If any wear is evident on the pinion, you must inspect the ring gear while you have the starter motor out. It's important to rotate the engine and inspect all parts of the ring gear. Here we have a ring gear removed from an outboard marine engine. We can see that there's excessive damage to the ring gear. In automotive, the ring gear can be removable, although typically it is attached permanently with the flywheel.
We're going to test the drive pinion on the armature. First thing we make sure is that we've got soft jaws in the vise. We can clamp it up. Without the soft jaws, we'll definitely damage the armature core. To test the drive, we use a hammer and punch. We don't have to bash the daylights out of it, just some gentle tapping. We can soon tell if it's going to slip or not. We also check the overrunning clutch to make sure that it freewheels properly in the opposite direction.
When inspecting the shift lever, check for excessive play in the pivot point. Also, here on where it makes contact with the drive, you should check that there's no square edges or wear. Here we have our main fields. Our first one is a permanent magnet field. We need to inspect to make sure that all of the magnets are still tight within the housing and that there are no signs of any cracks or damage. If there is any damage, they will need to be replaced. Here we have a series wound starter motor. We need to inspect for tightness of the fields again. We also need to inspect for any signs of discoloration within the fields. One of the first check we can do, check for continuity between our motor input to our brush. That ensures that our fields are still complete. Our second check we can do is checking for resistance between our input to the ground or to the casing of the fields to make sure there is no contact or no shorts. Here we have a larger example of a series wound field. If we look closely, we can see there's a bit of movement here. That's actually been caused due to overheating, and the insulation holding the field coils together has started to break down, and there's also some discoloration. Our largest one here is a compound wound field. Once again, inspecting for signs of wear on the pole shoes, make sure there's been no poling from the armature. We want to look for any signs of discoloration with our windings. We can check here our resistance of the shunt winding. And there we see, when I hold it steady, one ohm. Here we have our brush holder with our negative brush still attached. What we need to do is inspect the overall length of the brush and also inspect for signs of wear on the edges that could cause excessive movement within the holder. The other check we need to do is check that there's no continuity between the brush holder housing and the positive brush holder. You can see here, there is none. To our negative, of course, we have continuity. This piece of tooling here is known as an armature growler. It will test or allow us to test the windings on the armature. When I turn it on, I'll be placing a hacksaw blade the length of our windings and rotating the armature slowly. If there is any shorting between the windings, our hacksaw blade will start to vibrate. There we can see our armature is okay. Here we have an armature that we prepared earlier that's had some repairs attempted on it. We'll try and demonstrate the shorted windings. This armature needs to go in the bin. Here we'll be checking our armature is open circuit to ground. If we place 1 metre lead on the shaft and the other on our individual segments of the commutator, we can ensure that there is no continuity.